In this video, we are going to be learning how to determine the limiting reactant in a chemical reaction. We know that the coefficients in a balanced chemical equation tell us the proportion in which things react. They do not tell us what we started with and what we end with. They just tell us the proportion in which things react, the ratio. So this chemical equation tells us that for every 1 methane, we're going to use up 2 oxygens. So even though we start with 3 oxygen molecules, we only have enough methane to react with 2 of them. So this circle represents one reaction. After the reaction, I should have 1 carbon dioxide and 2 water molecules inside this circle. And I do. I have 1 carbon dioxide and 2 water molecules. But I still have this oxygen molecule left over, because we didn't have enough methane to react with it. So now we're going to assign some vocabulary to this. This O2 molecule represents the leftover excess. Since this is going to be our excess reactant, because there's some of it left over. Methane gets used up, so methane is our limiting reactant. It gets used up. So why is it called the limiting reactant? It's called the limiting reactant because it limits how much product can be made. It limited us to just what was inside the circle. We had enough oxygen to keep going, but since we were out of methane, we couldn't keep going. So now it's just a done reaction. Here's another practice problem for you. What is the limiting reactant in this scenario? Go ahead and pause the video and try to work this out on your own. After you are confident in your answer, go ahead and unpause the video. Okay, let's go over this. So, if we look at this before reaction box, we can see that for every 1 methane, we're going to use up 2 oxygens. 1 methane, 2 oxygens. 1 methane, 2 oxygens. So I'm going to run out of oxygen before I can react that methane. This is excess. O2 runs out. Therefore, O2 is the limiting reactant in this scenario. I have excess methane. When it is asking for the limiting reactant, you can at least narrow down your answer choices by eliminating the products. Remember that reactants are on the left-hand side. So you at least have to pick from one of the reactants. Now we are going to learn some mathematical approaches for deciding the limiting reactant. I'm going to be teaching you 3 different mathematical approaches to determining the limiting reactant. In one scenario, we're going to be comparing the amount of product. In scenario number 2, we're going to be comparing the amount of reactant. And then in the third one, we're going to be calculating the number of reactions that happen, much like we are doing in the pictures. And so the third method's most like the pictures that we've just been circling on. But in day-to-day scenarios, I mostly use method 1 or 2, and I interchange which method I'm using depending on what the question's asking. And so these are my 2 go-to methods because I can understand now which method is going to get me to my answer faster. So in our first approach, we're going to be calculating the amount of product we can make and then comparing the 2. This problem says how many moles of water can we make from 6 moles of hydrogen and 4 moles of oxygen. So we are given 6 moles of hydrogen and 4 moles of oxygen. Whenever we're given amounts of 2 different reactants, then we have to decide which one is the limiting reactant. So your clue that you're going to have to figure out the limiting reactant is that you have amounts of 2 reactants. So you have to determine the limiting. That way you know what amount of product you can make. The amounts are always limited by the limiting reactant. So if we assume that H2 is limiting, how much water could we make? If we start with our 6 moles of H2, we can cancel out our moles of H2, and we can go towards our product, because that's what our scenario is about. So moles of H2O is our only product. This is where I use the coefficients from the balanced equation, and that's going to work out to 6 moles of H2O. So this means that if I use up all of my hydrogen gas, I'll have 6 moles of water. But what if O2 was limiting? How much water could I make if I use up all of the O2 instead? I do have fewer moles of O2, so maybe all the O2 runs out first. Let's find out. So I'm setting up my conversion factor to switch between compounds, only now I'm not using that coefficient, I'm using that coefficient, which is a 1. And that's a 2. That's going to equal 8 moles of H2O. So that means that if I use up all of my O2 gas, I would have 8 moles of H2O. But I'm going to be stopping this reaction once I get to 6 moles of H2O, because at that point I'm out of H2. I can't make 8 moles of H2O because I'm out of hydrogen gas by the time I reach 6 moles. And so pick the smaller amount. And so that means that H2 is limiting. So the logic here is the most important part. So let me write that out. Once I make 6 moles of H2O, I'm out of H2 gas. Therefore, H2 gas is limiting, and I'll make 6 moles of H2O. So how many moles of water can I make? I'll make 6 moles of H2O. In this method, we're going to instead be comparing how much of one reactant we need to calculate the other reactant, so that we'll know whether we have any left over or not. So we're going to first calculate how many moles of oxygen gas we would need to react with all this hydrogen. And then we'll compare it to how much we actually have. So we're going to have to we just have to pick one of our reactants randomly. So I'm going to start with 6 moles of hydrogen gas and ask myself, how much oxygen would I need to react with this? So I'm going to be comparing hydrogen to oxygen. I need to cancel out my moles of hydrogen. I need to get into moles of oxygen. And that tells me I'm going to need 3 moles of O2 needed to react with all the H2. And so I have 4 moles of O2. So I compare. do I have enough? I have 4 moles, I need 3 moles. 4 moles minus 3 moles tells me that I'm going to have 1 mole of O2 left over. So I am going to use up 3 moles of O2. And I run out of H2. I have 4 moles of O2. So I'll have leftover. So H2 is limiting. So now we can calculate how many moles of water we'll need based on the limiting reactant. So now we can say, okay, if I have our 6 moles of H2, how many moles of water can I make? So where I pull out my molar ratio from the balanced chemical equation, and that's going to tell me that I make 6 moles of H2O. So the same answer we got before, but the logic to figure out which reactant was going to get used up is different. Now, I generally use the previous method when it's asking for the amount of product, but I generally use this method if it's asking me for how much of the excess is left over, because I know that in the logic for this one, I'm going to be calculating that along the way. So if I guess correctly here, then I'll know the amount left over immediately, and I won't have to do other calculations. For our third method, we're going to say that this whole thing is equal to 1 reaction. And then we're going to ask ourselves, how many reactions can we do? So it's the same problem as before. If I start with my 6 moles of H2, then for every 2 H2 moles that I do, I will have completed 1 reaction. And so that's going to tell me that I'm going to do 3 reactions. For my oxygen, if I use up all my oxygen, how many reactions will have happened? That's a 1 coefficient down here, and a 2 and a 1 coefficient here. So that tells me that I have enough O2 to do 4 reactions. I can't do the 4th reaction because I will run out of hydrogen after 3 reactions. H2 after 3 reactions. Can't do a 4th reaction. So that's how we interpret our math. Now that we know that H2 is limiting us to 3 reactions, how much water can we make? So this is our 6 moles of H2O, well, no, of H2, and we need to calculate our moles of H2O and get into, cancel out our moles of H2. So 2, that's a 2, and we end up with 6 moles of H2O, just like before. All right, for this next practice problem, we're going to need a calculator and our periodic tables because we're going to have to come up with chemical formulas and calculate some molar masses. before we can begin, we need to read this problem and write a balanced chemical equation from what it describes. So it says that I have 216 grams of aluminum sulfide. That's a typo there. So what's the chemical formula of aluminum sulfide? Aluminum likes to be 3+ cations, and sulfur likes to be 2- anions. And so a neutral ionic compound between the two is going to be Al2S3. And that's going to react with 173 grams of water. Water is H2O. And that's going to produce aluminum hydroxide. And so again, aluminum is 3+, and hydroxide is OH-. So this product is going to need 3 hydroxide ions. And then it's going to produce hydrogen sulfide gas, which is H2S. Now that we know our chemical equation, we got to balance it. I see 2 aluminums here, so I'm going to go ahead and put a 2 there. And then I see 3 sulfur, so I'm going to put a 3 there. And let's see, that's going to give me 6 hydrogens. That's going to give me 3 times 2, and that's going to give me 6 hydrogens. So that's going to give me a total of 12 hydrogens. So I'm going to put a 6 there. That's going to give me 6 oxygens, and that's going to give me 6 oxygens. So I should be balanced now. And now we can begin the problem. So let's see. What mass of the excess reactant is left over? So I don't know which reactant is going to be left over, so I just have to pick one and then calculate the amount needed of the other for comparison. So I'm going to pick this one and then calculate the amount of water I need to react with all that, just in case I get lucky. So that's 216 grams of Al2S3. And I need to get into moles, because the first thing I need to do is get into moles. And so I need to calculate the molar mass of Al2S3. So on my periodic table, I see that aluminum is 26.98 times 2 plus 3 times sulfur, which is 32.06. And so that's 150.14 for every 1 mole of aluminum sulfide. Good thing we got our chemical formulas right. Alright, the second thing we need to do is switch compounds. And so I'm going to be switching into water, the other reactant. This is like method 2 here. And so this is our molar ratio. And then it does ask me for mass, and so it doesn't take me that much longer to calculate the molar mass of something and just tack it on. So I might as well do that. That's 15.999 plus 2 times 1.008. And so that's going to be 18.015 grams per 1 mole. And that's going to be of water. So 216.0 divided by 150.14 times 6 times 18.015, and that's going to be 155.50 grams of H2O needed to react with all aluminum sulfide. How much do I have? I have 173 grams. So have minus need will give me leftover. So I have 173 grams of H2O. And if I subtract this amount, I'm going to end up with a positive number. So I'm going to do 173 minus my previous answer, and that's going to give me 17.495. And then I got to do my subtraction. Let's see, 4 sig figs here, so that's going to be 1, 2, 3, 4. 1, 2, 3, 4, so that's the 10th place. So that's going to be 17.5 grams of H2O left over. Now, this also means that I guessed correctly about what the limiting reactant was. If I had started with water and calculated how much aluminum sulfide I would need to react with all of that water, I would have ended up with a negative value here for the subtraction because I would have needed more than I had. But since we ended up with a positive amount left over, that's an indication that this water is excess reactant. And then the H2S was limiting. Here's a practice problem for you. Go ahead and pause the video and try to work this out on your own. Unpause the video when you are ready to continue. The problem reads, what mass of iron would be formed if 113 grams of aluminum was mixed with 279 grams of iron 3 oxide? Okay, let's do some math. So it says, what mass of iron would be formed if I do this? So it's asking for the amount of a product. So I'm going to do the first method that we talked about because that method might get me to my answer faster. So if I have 113 grams of aluminum and I look at my periodic table, aluminum has a molar mass of 26.98 grams per 1 mole. My balanced chemical equation tells me I'm going to use up 2 moles of aluminum for every 2 moles of iron that I make. It is asking for mass, and so I'm going to go ahead and calculate mass for this. In the homework, it stops at moles and has you compare the moles amounts, and that's fine too. But I'm just like, why not just go ahead and do it all the way? All right. I'm going to go ahead and get the second one set up as well before I type things into my calculator. So this is, I'm going to have to convert that into grams, not of aluminum, that's iron oxide. And then I'm going to need the molar mass of that. And so that's 55.85 times 2 plus 15.999 times 3. And so that's 159.697 grams per mole. Then according to my balanced chemical equation, that is a 1 coefficient. And that's going to give me 2 moles of iron. And then I can use the same grams per mole for the iron that I have just above. Okay, so now we have our 2 setups, and so let's go ahead and compare. And so that's 279 divided by my previous answer times 2. That's not times 2. Times 2 times 55.85. And so that's going to tell me that I have 195.146 grams of iron possible if I use up all of my iron oxide. What about in this first one? That's 100. Okay, fine. Gotta hit enter first. Okay, 113 divided by 26.98 times 2 divided by 2 times 55.885. And so that's 233.6 0.91586 grams of Fe from that. So how do we interpret this math? So if we look at this and we're trying to use up our 113 grams of aluminum and our 279 grams of iron 3 oxide, kind of like starting a race. And then after we make this, that should say 195 grams of iron, then we run out of our Fe2O3. And we had enough aluminum to keep going, but we're going to run out of our iron. And so we're going to run out of iron and we're going to make 195 grams of iron because we need 3 sig figs.